The last section for this unit that I'd like to cover is just going over some basics about vectors when we move from 2 dimensions to 3 dimensions. As we learned back in chapter 6, we have vectors written with i's and j's. And i's and j's meant horizontally and vertically respectively. But now that we've got 3 dimensions, we've got to have a third variable called k. So now we're going to be talking about i's, j's, and k's instead of just i's and j's. When we look at component forms of vectors, previously we had x's and y's, now we've got x, y, z. You're going to see in the section that all our properties are going to be the exact same as we had back in chapter 6 with the addition of a z component, just like we saw back earlier when we converted from 2 dimensions to 3 dimensions with spheres and ellipsoids. So just as we had before, a unit vector is defined as a vector divided by its magnitude. So you'll take your vector when it's in component form and divide each of the components by its magnitude. So the first thing we want to do is we want to find the component form and magnitude of a vector having an initial point in here and a terminal point here in space, and then find a unit vector. So to find the component form, we take terminal minus initial. So here I take terminal, which is 3, minus the initial. 3 minus 7 is negative 4. 14 minus 8 is 6. And negative 19 minus a negative 2 is a negative 17. So we subtract our x's, subtract our y's, subtract our z's. To find our magnitude, in the previous chapter we had the square root of x squared plus y squared. But now that we're in 3 dimensions, we apply this distance formula in 3 dimensions with the z piece. So now it's x squared plus y squared plus z squared, all underneath the square root. And since in my component form I've got x, y, and z, it's a straight plug-in. Negative 4 squared plus 6 squared plus negative 17 squared, all underneath the square root, is the square root of 341. The final piece then is taking a unit vector in the direction of v. So to find a unit vector, I take my vector, which is in component form, which I found right here, and I divide by the magnitude. And when I divide by the magnitude, every piece of the vector is divided by that magnitude. So the x, the y, and the z are all divided by the magnitude. The second concept is the dot product. We talked about the dot product as being a result of multiplying 2 vectors together, and with the dot product we end up with a scalar instead of another vector. When we did the dot product earlier, we said multiply the x's, multiply the y's, and add them together. Now we're looking at multiplying the x's, multiplying the y's, and multiplying the z's, and adding all 3 of those pieces together. So here, finding the dot product of vector u and vector v, notice I still have only 2 vectors I'm dealing with. Some students might think, oh, since I'm in 3 dimensions, I need 3 vectors. It's still just 2 vectors, just that I've got 3 pieces. So to find the dot product, we'll multiply the x's, so 5 times 5, which is the first piece here. Multiply the y's, 4 times negative 2, which you've got right there. And then 7 times negative 4, which we have right there. And we add all the pieces together, and we get negative 11. The last 2 concepts that we also looked at back in chapter 6 was the way we found an angle between 2 vectors. And you saw this formula. The cosine of theta is the dot product of u and v over the magnitude of u and v. Or we wrote it like this. Theta is equal to the cosine inverse of the dot product of u and v over the magnitude of u and v. So let's throw that down as well, because this is what we use more often. Exact formula that you learned back in chapter 6, and we're going to round to 3 decimal places. So if I have 2 vectors here, vectors u and v, I've got to do 3 things. First, I've got to find the dot product. Second, I've got to find the magnitude of both vectors. And then finally, I've got to plug into my formula and then get the calculator answer. So here, dot product of u and v, multiplying the x's, multiplying my y's, multiplying my z's, adding the results together, and I get 5. So that means 5 is going to be what I plug into this formula for the dot product. Then I find the magnitude, so x squared plus y squared plus z squared, all underneath the square root for u, gives me a square root of 10. And the same thing with v. X squared plus y squared plus z squared, all underneath the square root, gives me square root of 6. Plug those two guys into the formula, and then you take that whole piece and put it into your calculator. No need to rationalize the denominator, no need to simplify, just plug that directly into the calculator since the calculator will do all the simplification for you. The last concept then is looking at orthogonal versus perpendicular versus neither. And when the dot product of two vectors is 0, we can say that the vector is orthogonal or perpendicular. Reason for that is if I have up here the dot product as being 0, 0 over anything is 0, and the cosine inverse of 0 is 90 degrees. So that's why if we have the dot product, we can say vectors are orthogonal or they're going to be perpendicular. If vectors are parallel, they differ by a constant. Same thing as 2 dimensions. Only this time we're going to have to check for 3 pieces, all the same constant. So here I want to know if u and v are parallel, orthogonal, or neither. We've got 2 tests. First we test for the orthogonal. And we'll know we've got orthogonal vectors if the dot product is equal to 0. So dot product is multiplying the x's, multiplying the y's, multiplying the z's, and adding the 3 pieces together. And you can see in this example, the value is negative 24, which is not orthogonal because it's not equal to 0. So we can rule out orthogonal. We then do parallel, and we divide each of the components of the vector. So we divide the x components, divide the y components, divide the z components. And I can see if I divide my x's, my y's, and my z's, I get positive 1/2, negative 1/2, negative 7/2. Since all 3 of those are not identical, they are not parallel. I would need it to be 1/2, 1/2, 1/2, or negative 1/2, negative 1/2, negative 1/2. All 3 are different, so they're not parallel, so then I can see it's neither. So as you can see, this section is a lot like what we did in Chapter 6, only now we've expanded to 3 dimensions, which adds a z component to the dot product and the magnitude and the component form, compared to what we had back in Chapter 6 when we only had 2 dimensions.